Greetings, ma'am. I, Pallab Baruah, along with BIDIT KALITA, is going to present on the topic entropy and its applications. Here, we shall look up into what is entropy and what are its theoretical applications and what daily life observations we see from entropy point of view. Now, starting with the introductions, as we know, entropy of a quantity of heat which shows the possibility of conversion of that heat into work. We know entropy is a thermodynamic property. It can be viewed as measure of disorder. That is, more disorganized a system, the higher its entropy. Now we can see the properties of entropy. For an isolated system, the entropy, which is ds, always greater than equal to 0. For a reversible process, the entropy remains constant, that is ds equal to 0. We know for an irreversible process, ds always greater than 0, that is ds always positive. Entropy cannot be calculated in an irreversible path. For a calculation, the irreversible path must be replaced by a reversible path with same endpoints. Now I would like to ask BIDIT to continue with the applications of entropy.
Thank you, Pallab. Now, starting with the first theoretical application of entropy, we have mixing of two fluids at different temperatures. Now, let us assume two subsystems, 1 and 2, having mass m1 and m2, specific heat C1 and C2, and temperatures T1 and T2 respectively. And they are separated by a removable partition and are contained in an adiabatic enclosure. Now let us assume that these two fluids are allowed to mix together by removing the partition until the final equilibrium temperature Tf is reached. Here T1 is greater than Tf is greater than T2. Now as the system is isolated, therefore the energy interaction is confined to the two fluids, and we have M1C1 into T1 minus Tf is equals to M2C2 into Tf minus T2, and the final temperature Tf is given by M1C1 T1 plus M2C2 T2 divided by M1C1 plus M2C2. Now the entropy change for the subsystem 1 delta S1 is given by M1C1 ln Tf by T1. Here the capital T represents the temperature in Kelvin. Previously the small letter t represented the temperature in Celsius. Now as Tf is less than T1, therefore delta S is less than 0, because we know that log A by B is equals to log A minus log B. Similarly, delta S2 will be given by M2C2 ln Tf by T2, and this time delta S2 will be positive as Tf is greater than T2. Now the total entropy of the system, that is delta S universe, is given by the addition of delta S1 and delta S2, which is again given by M1C1 ln Tf by T1 plus M2C2 ln Tf by T2. Now since this mixing process is actually happening, it is not like impossible, therefore delta S universe must be greater than or equal to 0. Now we will see that this mixing process is irreversible with the help of entropy. Now since entropy cannot be calculated for an irreversible process, for calculation the entropy of the irreversible path must be replaced by a reversible path with the same endpoints, that is on which the integration was performed. Now let us assume that m1 equals to m2 is equals to m and c1 is equals to c2 is equals to c. Therefore delta S universe will be given by mc ln Tx square by T1 into T2, and the final temperature Tf will be given by T1 plus T2, and thus this delta S universe equals to 2mc ln T1 plus T2 divided by 2 divided by root over T1 into T2. Now if we observe closely and see that T1 and T2 are two different temperatures, because this is what we assumed. So if T1 and T2 are different terms, then T1 plus T2 divided by 2 is the arithmetic mean of T1 and T2, and root over T1 into T2 is the geometric mean of T1 and T2. Now since arithmetic mean is greater than geometric mean, Therefore, T1 plus T2 divided by 2 is greater than T root over T1 into T2. Now this makes the delta S universe positive, that is greater than 0, and thus the mixing process is irreversible. This process might have been reversible if these temperatures T1 and T2 been equal. But since we are discussing mixing of two fluids at different temperatures, therefore the process is irreversible. Now coming to the second theoretical application of entropy, we have the transfer of heat through a finite temperature difference. Now let us assume flowing of heat from reservoir A at temperature T1 to reservoir B at temperature T2. That is, here we assume T1 is greater than T2. Now since the reservoir A is supplying the heat, therefore delta SA, that is the entropy change for the reservoir A, will be negative and will be equal to minus Q by T1. And similarly, since the reservoir B is accepting the heat, therefore delta SB equals to Q by T2, and it is positive. The rod connecting between the reservoirs do not suffer any entropy change because once in the steady state, its coordinates do not change. Therefore, for an isolated system comprising of the reservoirs and connecting rod, and since entropy is an additive property, we have delta S universe equals to delta SA plus delta SB. And putting the formula of delta SA and delta SB, we have delta S universe equals to Q into T1 minus T2 divided by T1 into T2. Now here we assumed that T1 is greater than T2. Now if we put T1 is greater than T2, therefore we will have delta S universe is greater than 0. That is, it is an irreversible process. Had T1 been equal to T2, therefore delta S universe would have been equal to 0 and the process would have been reversible. But if T1 was less than T2, delta S inverse would have been negative and the process would have been impossible. This is basically the second law of thermodynamics, which tells us that without any external aid, transfer of energy from cooler body to a hotter body is not possible. Now coming to the third theoretical application of entropy, we will be discussing maximum work obtainable from two finite bodies at temperatures T1 and T2. Now for that, let us consider two identical finite bodies of constant heat capacity at temperatures T1 and T2 respectively, where T1 is greater than T2. Now the final temperature Tf reached during the contact of two bodies will be maximum when the system is not doing any work. And putting that condition into the energy interaction formula, we will obtain Tf is equals to T1 plus T2 divided by 2. Now, if a heat engine is brought to operate between the reservoirs, that is the bodies which are now acting as thermal energy reservoirs, wherein it takes heat from the body 1 and heat is rejected to the body 2 after the work has been done by the heat engine. It is seen that the maximum possible work that can be done by the heat engine is when the final temperature Tf is the lowest. As work is delivered by the heat engine, the temperature of the body 1 decreases and therefore the body 2 increases until the heat engine stops operating at final temperature Tf. Now let us assume that the bodies remain at constant temperature and do not undergo any change of phase. The working fluid in the heat engine does not go any entropy change. So these are the assumptions. Now the total heat withdrawn from the body 1, that is Q1, is given by Cp into T1 minus Tf, and the total heat rejected to the body 2 is given by Q2 equals to Cp into Tf minus T2, where Cp is the heat capacity of the two bodies at constant pressure. Now the work done by the heat engine is given by W is equals to Q1 minus Q2, which is equals to Cp into T1 plus T2 minus twice Tf. Since Cp, T1 and T2 are already known for the given system and can be considered constant, thus W depends only on Tf, that is the final temperature. Now W is maximum when T is minimum. We already established that. Now for body 1, entropy change is given by delta S1 equals to Cp ln Tf by T1, and similarly for body 2, delta S2 is given by Cp Tf ln Tf by T2. Now in case of the working fluid, we know that there is no entropy change, therefore integration of delta S of the fluid is equal to 0. Now from entropy principle we know that entropy always increases, it never decreases, therefore Cp ln Tf by T1 plus Cp ln Tf by T2 is greater than or equal to 0. Now since the value of this part Cp ln Tf square by T1 into T2 is minimum when Tf is minimum, since these three are constant, so this will be minimum, that is equals to 0 when Tf is minimum. Now we need the minimum value of Tf, therefore we need this equation Cp ln Tf square by T1 into T2. Thus equating this, we get Tf equals to root over T1 into T2. Thus, for the work done by the heat engine to be maximum, Tf, that is the final temperature reached, must be equal to root over T1 into T2. Now putting the value of Tf in the equation 1, that is this equation, we get maximum work done W max equals to Cp into whole square of root T1 minus root T2. Now we will come to the daily life observations we do and try to relate it with the principle of entropy. Now the studies show that the universe tends to move towards highest entropy, and this is basically the reason we see the melting of ice under normal room temperature and not solidification of water into ice. This is the same reason we see dissolving of salt or sugar, and this is the reason we see smoke coming out after lighting a match. It expands and it does not remain concentrated or organized at a place. Now this bursting of a water balloon is a great example of entropy in action. Since gravity is acting, the water should have simply fallen down, but it does not. It tries to expand in all other directions possible, and this is because of entropy in action. It tends to move towards highest entropy, and thus, as we can see, the water droplets expand in every direction possible. So this was basically the topic entropy and its application.